Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspire Teens Grade 11 Physics. Okay, in today's lesson, we are going to be continuing with stoichiometry. Okay, we'll be doing limiting reagent, and I'll be teaching you guys how to use a Rice table. Okay, so just to recap, we're just going to discuss limiting reagents once again. Okay, so we're going to have a look at this reaction. Let me just move this. Okay, let's do this. Okay. So what we're going to do is we're going to have a look at this reaction, okay? And we're also going to rediscuss limiting reagent graphs, okay? And what do we mean when we say limiting reagent, okay? What do we mean when we say excess? Because together with the limiting reagent comes an excess as well. So whenever we have a chemical reaction, okay, so within certain chemical reactions, okay, we have a certain amount of a certain amount of reactants to form a certain amount of product, okay? And that is set according to this chemical formula. So this chemical formula, being that it's balanced, so this one is balanced, okay? For this specific reaction will help us to determine how many moles of each reactant do we need and how many moles of product will we form when we use these amount of reactants. Okay, so the chemical reaction holds true to that. So for example, in this case, it's 1 mole of magnesium and 1 mole of H2SO4 that's going to form 1 mole of magnesium sulfate and 1 mole of hydrogen. Okay, in this case, it's just the molar ratio is 1 for all of them. Okay, however, remember that moles does not necessarily mean the same amount of the same mass of each substance, right? So for example, 1 mole of magnesium is a different amount to 1 mole of H2SO4. Okay, what's true is that they have the same amount of particles, right? Because that's how we defined 1 mole. So what we need to understand, if I want to put it in basic terms, all right, let's just say that we need 1 mole of magnesium, like this says, to react with 1 mole of H2SO4. Okay, so what happens if I have, okay, this is not a great example. Okay, let's do this. Let's change this molar ratio to 2. Okay, it's not correct, but just for the sake of the explanation, we're going to change the molar ratio of H2SO4 to, no, 1 doesn't work. Let's do this. Let's change this to 3, and let's change that to 2. Okay, so this is saying that 3 moles plus 2 moles, okay, is going to give us the product. That's the basic understanding that we want to take, okay? Even if we just have to ignore this for now, okay? Let's discuss this. We're saying that 3 moles plus 2 moles gives us a product, okay? 3 moles of one substance plus 2 moles of another substance gives us a product. So what happens if, okay, let's call this product A and product B, sorry, reactant A and reactant B to form product. Okay, so what happens if I bring 15 moles of A, okay, and I add it with 14 moles of B. Okay, how much product do I end up forming? Okay, so if we have to look at this, okay, we understand that we need to take 3 moles of product of reactant A and 2 moles of reactant B to form a single product. Okay, so here's one product, this forms one product, and this forms one product. Okay, so now in this case, if we have 15 moles of A, okay, 15 can divide by 3 5 times. So we can have a total of 5 3 moles to form our product. Okay, and from here we can form 7. Okay, I hope that this is making sense. So all I'm saying is that if I take a total of 15 moles of A, right, if I am reacting, right, if I have a container, okay, and I take 15 moles of A and I react it with 14 moles of B. Now remember, in order for this reaction to occur, okay, to form our product, for every 3 moles of A, we need to use 2 moles of B. Okay, so we use our first 3 moles here and our first 2 moles here to form one product. Here we'll be left with, we minus 2, we'll be left with 12. Here we'll be left with 12 as well. And we carry on subtracting 3. So that's the idea that I'm getting at here, right? Grouping these in order to form the reactant. So here, right, the amount of reactants that I can form for this reaction from 15 moles would be 5. Because 15 divided by 3, okay, 5. I can get 5 bundles of 3 moles. Okay, so in order for this reaction to occur, right, I can get 5 bundles of these 3 moles that I need for the reaction. Okay, however, here I have 14 moles in total. So because it only takes 2 moles for that reaction to occur, I can form 7 of those bundles. Okay, here I can form 5 3 moles. Here I can form 7 2 moles. Okay, now because we react perfectly 3 moles with 2 moles, okay, we will only be able to create 5 products because we are limited by the amount of reactant A that we have. Okay, because here we can form 7 of reactant B, but we can only form 5 of reactant A because reactant A requires 3 moles while reactant B only requires 2 moles. Okay, so in this case, we can form 5 reactant A's, but 7 reactant B's. Okay, so because of this reason, we won't be able to form all 7, not all 7, not all 14 rather, not all 14 moles of reactant B will be used up. Okay, so what can we do? In this case, right, we form 5 times reactant A plus, okay, 5 reactant A's plus 5 reactant B's. Okay, remember, when we talk about reactant B, we're talking about, when we're talking about reactant A, we're talking about reactant A, 3 moles of it. So 5, 3 moles of reactant A, and 5, 2 moles of reactant B's. Okay, and together they are going to form 5 products. Okay, and we'll be left over with, because here we could form 7 times 2 moles, and here we could form 5 times 3 moles. Okay, here we'll be left over with 2 times 2 moles of reactant B. Okay, so because this is a 3 mole to 2 mole ratio, so we need 3 moles of reactant A to mix with 2 moles of reactant B, okay, to form a singular product. Okay, so when you have a mixture, when you want a reaction to occur, just say you are given 15 moles of reactant A and 14 moles of reactant B, and you're asked to determine how much product will you form. Okay, so this is where the concept of limiting reagent and access comes in. Okay, because one of the reactants, okay, is going to limit your reaction. Sorry, just give me 1 second. Okay, one of these are going to limit your reaction. And how do you determine that? So from our 15 moles of reactant A that we are given, we determine how many bundles can we form in order for our reaction to occur. So we know in our reaction we need 3 moles. So we group this 15 moles into 3 mole bundles. Okay, and we know that we can form 5 of them. okay? And then we group our 14 moles of reactant B into little bundles because we need them into 2 moles each, okay? So we can form 7 2 moles of reactant B. So we have 5 times 3 moles of reactant A, but we have 7 times 2 moles of reactant. Sorry, we have 5 times 3 moles of reactant A, and we have 7 times 2 moles of reactant B. Okay, so because we don't have enough reactant A, okay, we don't have enough of reactant A to react totally with reactant B. We only have 5 of these, but we have 7 of these. So the 5 of these are going to react with 5 of B, okay, because we don't have 7, essentially, okay, and we'll be left over with 2 additional moles of reactant B. Well, 2 times 2. Okay, and in this case, we can take those 5 moles of reactant A, react them with 5 moles, or not 5, but 5 times the 3 moles of reactant A, 5 times the 3 moles of reactant B to form 5 whole products. Okay, and here we have an excess amount of reactant B. And yes, as someone said in the chat, we will then consider this to be the limiting reagent. Okay, this limiting reagent, it limits the amount of product that can be formed. Because if we had to have, we have more reactant B to form more product, but unfortunately, reactant A, we don't have more of it to react with reactant B to form the product. So this is why we refer to reactant A as the limiting reagent. Okay, reactant A, limiting reagent, because it is the one that would finish first. If you have to mix reactant A and reactant B together, okay, 3 moles of A are going to react with 3 moles of B. Okay, so you start off with 15, then it goes to 12 if you're using 3 moles each time. Okay, then you use up 2 moles of reactant B at a time. So you react 3 moles of reactant A, 2 moles of reactant B, and you react them together to form one product. And the one that finishes first, the one that would deplete first, is going to be reactant A, okay, because we technically have more bundles of reactant B than we have of reactant A. So therefore, reactant A finishes first, okay, depletes first. We use it all up, okay, we use up all of reactant A, but we left over with a certain amount of reactant B, and that is known as the excess, the one that's extra. Okay, so that's the entire concept of limiting reagent, right? That remains true throughout, okay, even through this simplified explanation, right? So what you need to understand is that in chemistry, when we have a reaction, okay, and we have, let's just say, 2 reactants, okay, a certain amount of A would react with a certain amount of B, okay, but in chemistry, right, the way that the chemical reaction occurs, we need a specific amount of a certain substance to mix with a specific amount of a certain substance, okay? And if you don't have exact figures, okay, one is going to be extra. It's just like, yeah, I can't really think of another explanation for it, but that's how you should remember it. One is going to finish completely, and one you have extra of. Okay, because like, let's just say, for instance, here, even if we had to do it with a 1-to-1 molar ratio, if I have, so 1 mole of Mg has to react with 1 mole of H2SO4. If I have 7 moles of Mg and I want to react it with 5 moles of H2SO4, okay, remember this is a 1-to-1 ratio. So in this reaction, 1 mole of Mg reacts with 1 mole of H2SO4, right? So let's just say, okay, this forms, we can regard this as just one product, right? This entire thing is just one product, okay? So in this case, 7 moles of Mg and 5 moles of H2SO4, we have more of Mg than we have of H2SO4. And because it's a 1-to-1 molar ratio, 1 mole of Mg is going to react with 1 mole of H2SO4. So it's basically like ingredients for something, but you have extra left of one ingredient. Exactly, right? So, okay. So in this case, like I was saying, it's a 1-to-1 ratio. So you're going to react 1 mole of Mg with 1 mole of H2SO4. So as they react, right? You're going to use 1 mole reacting with 1 mole, then your second mole, then your third mole, then your fourth mole, then your fifth mole. Once you use up the fifth mole of H2SO4, you don't have any left over. However, you'll still have 2 extra moles of Mg, okay? And that is what happens. This is, you'll only be able to use 5 in the reaction because the reaction has a specific ratio, right? And if you think of it as ingredients, mixing ingredients, and you have an extra amount of something, you can't just add it into the mixture because you could ruin whatever you're making, okay? So in this case, you're only going to be able to react 5 moles of Mg and 5 moles of H2SO4. Okay, and here you'll be left with an extra amount of 2 moles of Mg, and that's known as the excess. Okay, yes, and it works exactly like a recipe, right? If you're following a recipe to create anything, like let's just say a cake, you follow the recipe specifically, right? You need to add the right amount of salt, the right amount of flour, the right amount of whatever else it takes to make a cake, right? And you're obviously going to mix it in that specific ratio. And there might be some ingredients which you have or you bought an exact amount of, or there might be some ingredients that you left over with an extra amount of, okay? So the one that finishes in a chemical reaction is known as the limiting reagent because it limits the amount of product you can form, right? If you had to have more of the limiting reagent, you would be able to form more product, okay? So for this example, if we had 7 moles of H2SO4 initially, we would be able to form 7 products. But now we only formed 5 products, okay? Because we don't have enough Mg to react with more of that H2SO4. Okay, so I hope that makes sense. Okay, so just to reiterate this one, we have a 1-to-1 molar ratio of Mg and H2SO4. Okay, we have initially 7 moles of Mg and 5 moles of H2SO4. And because 1 mole reacts with 1 mole, when they react, we will only be able to form a total of 5 products because the minimum mole, the smallest mole, is H2SO4. And you basically can only form as much products as your least reactant. Okay, you're going to form as much products as your least reactant. So because you have 5 moles of H2SO4, it can only react with 5 moles of Mg. That would leave us with an extra amount of 2 moles of Mg at the end of the reaction. And we can only form 5 products. If we had to have an extra 2 moles of H2SO4, we would be able to form 7 products. Okay, this is with a 1-to-1 ratio, and this is with a 3-to-2 ratio. Okay, so let's have a look at the graphs. Okay, I'm sure you'd be able to guess which graph is for which, but one of these graphs is for excess, and one of these graphs is for the limiting reagent. So this one at the bottom is for the limiting reagent. Limiting reagent, limiting reaction, that's the same thing. Reaction refers to the reaction, reagent refers to the specific reactant. That's the limiting reagent. Okay, this is the limiting reagent because we can see that it depletes. Okay, it is used up completely, let's just say at time t. However, we can see that this is the excess graph because when the reaction completes at time t, we still have an amount left over because these are values. So if this is a mass versus time graph, okay, grams versus time graph, okay, we can see that we start off with a certain amount of this reactant, and if the reaction ends at t, or we can even understand that the reaction ends because this plateaus, right? We don't use up any more of this. It doesn't, you can see it's decreasing until it gets to time t where it just remains constant. That means that we were using it up until the reaction completed, and then we didn't need to use any more. And we can see at the same time interval t, okay, for the limiting reagent, it goes to 0 because it is used up completely. Okay, so these are the 2 different graphs that represent either excess or limiting reagent. Okay, both are reactant graphs, okay, because both the excess and the limiting reagent represent reactants. Okay. And yeah, so you could sometimes in questions, you'll be given a graph and you need to understand whether that specific graph is the axis or it's the limiting reagent. Let's see if there's anything we need to discuss. Okay, let's have a look at this note. It says that if one reactant is in excess, it means that there's more than enough of it. If there are only two reactants and one is in excess, it means that the other is the limiting reagent. So that's something you should note also. When we're dealing with limiting reagent, we'll be dealing with two reactants, okay? And if one is the excess, definitely the other one is limiting reagent. And if one is the limiting reagent, then definitely the other is in excess. Okay, so these are maybe just fancy terms, excess and limiting reagent, to describe what means that you have extra of one and you have just enough of another. Or you have more of one than you have of the other. Okay, but yeah, you must. So when it's a 1-to-1 mole ratio, perhaps it's easier to understand. But obviously, in a chemical reaction, it's not always a 1-to-1 molar ratio. So here we have an explanation in terms of the different moles. Okay, which is also important to understand. Okay. I hope that you guys understand that. Please let me know if you have any questions or if you want me to clarify anything, then we can go through that concept again, because you have to understand that concept, just the basic understanding of what a limiting reagent is and what is excess, okay, and the simple understanding of it, right, when we explain it, not in terms of chemistry, okay, before we can actually get to the calculations. Okay, so let us go on to the calculations and let us do an example of a limiting reagent question, and we're going to learn the Rice table, okay, and we're going to learn how to answer a limiting reagent question. Okay, let's have a look at this. It says that an example, an 8.4 gram sample of nitrogen reacts with 1.5 grams hydrogen. The balanced equation is N2 plus 3H2 gives us 2NH3. Determine which reactant is the limiting reactant and the mass of ammonia that can be produced. So for both question A and question B, they can be answered directly from the Rice table. Now, some of you might have not learned the Rice table and you just use basic stoichiometry. After learning the Rice table today, if you prefer to use your basic stoichiometry and if it works for you, then you are free to continue using it. However, I do recommend using a Rice table because it is a more simplified structure. It's more simplified and more structured, okay, and you'll be using a Rice table in acids and bases. You'll be using a Rice table in chemical equilibrium next year and this year technically for acids and bases. So I would recommend that you get used to a Rice table. Okay, so let's have a look at how we answer this question utilizing our Rice table. So the first thing we can do is write our chemical reaction above. Okay, and we can go through what each of these letters represent. So the first one is R, okay, and R stands for the ratio. Okay, so when we talk about ratio, we're talking about molar ratio. Okay, so when we talk about molar ratio, we're talking about the coefficients of each chemical formula. So the ratio here is a 1:3:2 molar ratio. 1:3:2. So basically we have 1 mole of N2 that needs to react with 3 moles of H2 to form 2 moles of NH3. Then we talk about I. Now I stands for the initial amount. I stands for initial. And initial is basically before the reaction occurs. The initial is before the reaction even occurs. Okay, so initially, how much do we have? Okay, and we'll discuss it in terms of that example in a second. Or maybe we can discuss it one time, or maybe not. Let's discuss these. This stands for change. Okay, and this stands for end. Now, when we look at our sentence, okay, one thing that's very important in chemistry is actually the English, the written part of the chemistry. You have to understand what they are telling you. And you'll see in this case, you have to understand whether you are given the initial, whether you are given the change or whether you are given the end. Okay, so what happens is an 8.4 gram sample of nitrogen reacts with 1.5 gram of hydrogen. The balance equation is as follows. Now, a hint to you that firstly, you don't know if all of the nitrogen given reacts with all of the hydrogen, right? Like they say 8.4 grams reacts with 1.5. Now, we don't know if it's a 1-to-1 ratio. Actually, we know what the ratio is, right? However, like, for example, we don't know that we have 1.5 grams of hydrogen and it's going to react with 1.5 grams of nitrogen. That's not something that we have knowledge of. Okay, that's not something we expected to have knowledge of. So just from this information, we cannot determine whether all of the nitrogen is going to react with all of the hydrogen, nor can we conclude that all of the hydrogen is going to react with all of the nitrogen. This is not something that we know, and it's not something that we can assume. Okay, that's where the rice table comes in. Okay, that's where the whole understanding of limiting reagent comes in. What we should understand is that one of these reactants reacts completely and the other is finished up. Okay, sorry, the other we have extra of. One of these react completely and the other is in excess. Okay, so now we need to determine which is which. But we do know initially we have this amount. So initially we have 8.4 grams of nitrogen and we have 1.5 grams of hydrogen. That's the initial information that we have. Now, that's how we understand also that it's initial, okay? Because they don't tell us, okay? You see, you must look out for the keywords also, and you'll see once we get to grade 12, we'll look out for keywords more carefully, right? But this word reacts, right? It doesn't say completely reacts, okay? It gets a bit tricky, but for you, it's just safest to assume, especially if they ask limiting reagent. What you want to do is look out for a graph that shows you that maybe one of the reactants are limiting reagent, or if they ask the question, which is the limiting reagent, then of course, this is not a reaction where both reactants react completely, okay? So when they use the word react, it does not mean completely reacts, okay? Sometimes when they use the word completely reacts, it's only for one reactant, okay? But then they'll say, like, for example, 8 grams of nitrogen completely reacts with excess 1.5 grams of hydrogen. Okay, in that case, you know, immediately you know which one is the limiting reagent, which one is the excess. Okay, but I'm just telling you now, do not ever assume that all of it reacts, right? Your understanding should be, okay, initially I have 8.4 grams of nitrogen and I have 1.5 grams of hydrogen and I'm going to put them together. I don't know how they react, right? I don't know how much of each is going to react with how much of each and so on. Right? You're not aware of, but you know that initially you have that amount. One of it is going to react completely, one of it is going to be excess. So that's how you should understand that the information given is actually your initial amounts. Now, you're not going to put it here in grams. Okay, you actually have to convert to moles. So keep in mind that this entire table, okay, is in moles. Okay, actually just from initial to end, because technically R is just numbers, molar ratio. So all of this is in moles, okay? So you can only input, you should only input moles into this rice table, okay? So this is what it stands for: ratio, initial, change, and end. So we're going to try and fill in as much of this table as possible. So what we want to do first, okay, we're busy with A, right? This is the first step. We're still determining which is the limiting reaction. And now I'm going to show you how we determine it. The first step is we have initial amounts. We have 8.4 grams of nitrogen. Second. Get a memo so it can go faster. Okay. We know the mass of nitrogen and we know the mass of hydrogen, so we can go convert those to moles using this formula. N is equal to mass over molar mass. So for N2, right, mass over molar mass, the mass given for N2 is 8.4 grams. The molar mass of N2, if you have to look at the periodic table, 14 is for nitrogen, multiplied by 2, you get 28. This gives you an answer of the moles of nitrogen. So let's do this if you want to consider it the moles. we can do this, moles, and then put bracket of nitrogen. The moles of nitrogen, 8.4, the grams, the mass given divided by its molar mass, we get an answer of 0.3 moles. Then we want to determine the moles of hydrogen, the other product, right? The moles of hydrogen, and this is going to be 1.5 divided by the mass of hydrogen, which is 1 times 2, because it's diatomic. 1.5 divided by 2 gives us 0.75 moles. So this is what we can put into our rise table. So initially in moles, okay, we have 0.3 moles. We don't have to put the symbol as long as we can represent it there. I mean the unit. We have 0.3 moles of N2 and we have 0.75 moles of H2. Okay, so I hope you guys are with me so far. Initial is what we're going to put initially into this table, and we can only put moles into this table. So therefore, we convert the mass given to us to moles. Now we're going to use trial and error because they don't tell us, there's no graph that indicates to us which one is limiting, nor do they tell us which one is the limiting reagent. So now we have to determine for ourselves using calculations, which is the limiting reagent, which of these two are the limiting reagent. Is it nitrogen or is it hydrogen? We're not going to guess. We're going to use a trial and error calculation. So what you want to do is you want to assume that one of them is the limiting reagent. So you start off with the first one, and maybe as you go along, you'll get better at assuming which one is the limiting reagent. Okay, so we're going to assume that nitrogen gas, this is what we're going to trial and error. We're going to assume that nitrogen gas is the limiting reagent. That's what we're going to do right now. So we have to understand that the limiting reagent will always end in 0. That's the key concept that helps us to determine which one is the limiting reagent. We have to understand the limiting reagent always ends in 0. At the end of the reaction, you have nothing of it left over. The other one you'll have excess of. So we are going to assume that N2 is the limiting reagent. And you always end up with 0 on the limiting reagent. Now let's quickly discuss change. Now, we have initially a certain amount. Change is the amount that actually reacts. Okay, so we know for a fact that not all of one of these two are going to react. Okay, but in change gives us, in change, what do we put? We put the exact amount that reacts. That is the change. Some of you might learn like a Mr. Sufi table, molar ratio, start, used, formed, end, something like that. Okay, it's a very similar concept. Instead, here we just have, instead of MR, we have R. Instead of S, we have I. Instead of used and formed, we represent it in one called change. Okay, just called change, because a change is either used or formed. Now, the change that happens to reactants is a negative change, right? Because we use up reactants. So here, you should minus this change to give you the end, because initial, the change, and then end. So you say initial minus change gives you end. And the same thing happens for this reactant. Initial minus change gives you end. However, for the product, initial plus the change gives you end, because you form products. Okay, so for those of you who perhaps learned the Mr. Sufi table, right, formed would be what you add, and then used would be what you subtract in the change. Okay, so these are important things this is important that you need to understand. You subtract on the reactants part in change, and you add for the products part, okay, in change as well. Okay, so now 0.3 initially and 0.75 initially. How did we get those amounts? We used calculations to determine those amounts, because we know that initially that's how much of nitrogen and hydrogen we had. Okay, so that's why we put the initial amounts there. The next thing that we were busy with is we are trying to determine which is the limiting reagent. And I told you we are going to use trial and error. So the first, we're going to assume that one of them is the limiting reagent, and I am assuming that nitrogen is the limiting reagent. Now we understand how we got this initial. Why are we putting 0 by end? We are putting by 0 by end because we are assuming that N2 is the limiting reagent, and the limiting reagent will always end in 0. So if we start off with 0.3 moles and we end off with 0 moles, how much changed, or how much did we use? Of course, we used all of it. So that's why we would have to subtract 0.3 moles in the change. Okay, so this is making sense so far. We're assuming that N2 is the limiting reagent. We start off with 0.3. That's the information we got from the question. The limiting reagent would always end in 0. And in order to start off with something and end up with 0, you have to use all of it. So that's why now we can complete this value in the change and put 0.3. Okay. Now what we can do, there's something really important that is the key to answering a rice table. The only place where you can use the molar ratio is here. Now you're going to hear me say this about 678 billion times because it's important. Technically, once you've gone in the change, once you've gotten your first value in the change, it's like you've solved the entire question. That's how important it is to get to the change. Okay. Once you got your first value in change, it's like you've solved the entire question. Okay. There's one thing I want you to take note of here. This is a 1:3 molar ratio. 1:3. But if we look at this initial amounts, they don't follow the molar ratio. The initial amounts don't follow the molar ratio. Why? Okay, look at it. It's a 1:3 molar ratio between nitrogen and hydrogen. But when I multiply this guy by 3, I get 0.9. So they don't actually, or if I divide this by 3, I don't get 0.3. They don't follow the molar ratio. Okay, and that makes sense because remember initially, right, we don't have an exact amount of reactants. We are just given a certain amount of A, a certain amount of B. One of them is more than the other that we need, okay? And one of them is going to get used up first. Now, remember, when a reaction occurs, when a chemical reaction occurs, it always occurs to this molar ratio. It will always obey this molar ratio. 1 mole of one reacts with 3 moles of another to form 2 moles of a product. It will always obey that ratio. The chemical reaction, when it occurs, even in an actual real life scenario, it will always follow this molar ratio. Okay, that's when the reaction occurs. But initially, the reaction is not occurring. We are just given a certain amount of N2 and a certain amount of H2, and then they react. Now, you see, initially, they won't follow the molar ratio because we just have a certain amount of one and a certain amount of another. But remember, when they react, of course, they're going to react according to the molar ratio. So in that case, that's why the only place where we can use molar ratio is in the change, because in the change, this is where they react. This is where the reaction occurs. In the change, this is where they react. So therefore, that is the only place where we can actually use the molar ratio. So if you look here, the initial amounts don't follow the molar ratio, but we can use the molar ratio in change. So here it's a 0.3, it's a 1, it has a 1 molar ratio, it's a 1:3 molar ratio. So we divide by our own, multiply by the one we want. That's how we use molar ratio, by the way. Okay, we say the moles of, where's my chemical reaction? N2 are to the moles of H2. This is a 1:3 ratio. So 0.3 are the moles that we have for N2. Okay, so what you do to determine to use the molar ratio, because I always say the molar ratio, once you have the molar ratio is easy to use, right? You can always bounce across, meaning if you have the moles of this, you can easily get the moles of that. You can easily get the moles of that, right? You just bounce across using the molar ratio. So there's a 1:3 ratio. You always divide by the molar ratio that you currently have. So you want to convert these moles into the moles of something with a different molar ratio. You divide by its own molar ratio and multiply by the molar ratio that you want. So divide by 1 times by 3, that gives us 0.9 moles of N2. Divide by your own molar ratio, multiply by the molar ratio that you want. Okay, so in this case, I can use the molar ratio. So like I said, that's why once you've solved for one of them in the change, you've solved for the entire question, basically. Once you in change, you solve the question. So I divide by 1, multiply by 3, that's going to give me the moles that I should put here, 0.9. Okay, so let's just recap. We had the initial amounts which we put in there. We used trial and error we assume that N2 is the molar ratio. So, we assume that N2 is the limiting reagent. So it has to end in 0. Always, limiting reagent always ends in 0. So therefore, if you end in 0, that means you use up all of it. Now, once we in change, that's the only place we can use molar ratio. The only place in which you can use molar ratio is change. Do not use it in initial, do not use it in end. The only place you can use molar ratio is in change. So once I have one amount in change, I can get all the amounts in change using the molar ratio. And that's exactly what I did, because I know I used up, hypothetically speaking, if N2 is my limiting reagent, I would have used up all of it. I used the molar ratio to get the moles here. I get 0.9. But now when we look at this, we see initially we had 0.75 moles of H2 and we used up 0.9 moles. That doesn't make any sense because we can't use up more than we started off with. So that means that you've chosen the wrong limiting reagent. That's when you go back and you assume that the other one is the limiting reagent now. So what did we find? We found out that there was more in change than there was initially, and that's incorrect. That just means that you've used the wrong molar ratio. So now we try, this is where the trial and error comes in. You try out the second one. Let's try out hydrogen. So let us assume that hydrogen is the limiting reagent. So if hydrogen is the limiting reagent, it's going to end in 0, definitely. However, so therefore, because it ends in 0, okay, if we start off with 0.5 and we end up with 0.5, we have to have used up 0.75. So we say 0.75 minus 0.75, and that gives us 0. That's correct. Now, where am I? I am in change, and once I am in change, I have solved the question. So once I'm in change, I know that I can use the molar ratio because it's the only place where I can use the molar ratio. So let's use the molar ratio. Okay, we can do all of this. We can keep all of this, I mean. Okay, so it's a 1-to-3 ratio. So here we have 0.75. So 0.75 moles of H2. We need to get the moles of N2. So we divide by 3, multiply by 1. So essentially just divide by 3. So 0.75 divided by 3 multiplied by 1 is 0.25 moles. So that means I can use molar ratio 0.75 divided by 3 multiplied by 1 to give me the moles in change of N2. This is 0.25. Now, if I look at my initial is bigger than my change, which makes sense. Let's do this, 0.25. So this is okay because I can start off with 0.3, use up 0.25, and then I'll be left with at the end 0.05. So here they could ask even what is the moles or the mass of the limiting reagent. Okay, so in this case specifically, we have now determined the limiting reagent. Okay, so this guy would be our limiting reagent because it ends up with 0. Okay, and this is the one that would be in excess. Okay, simply, it's even shown in the amount that they have in the end. You will always have no limiting reagent at the end, and you will always have a certain amount of the excess at the end. Okay, so yes, this is how we utilize a Rice table to determine which is the limiting reagent. Right, you'll see it might be daunting now and might seem tough, but it's a simple method that you'll get used to very fast. Okay, even the trial and error, you can start doing the trial and error in your head. You don't even have to write it out. Okay, so what you can do in your head, you say, okay, N2. You know that, okay, initially you have 0.3 moles of N2, right? If you're going to put 0.3 here, you're going to have to divide it by 1, multiply it by 3, and then you'll see that that amount is bigger than what you started off with H2. So you're like, okay, if it's not this one, it has to be this one, and you go ahead and do your work and immediately treat this as the limiting reagent. So we start off with initially 0.75. We have to end in 0 because we end in 0 with the limiting reagent. So if you start off with a certain amount and you end up with 0, that means you used all of it. Now, once you in change, you've solved the question. The only place in which you can use molar ratio is in change. So you can divide by 3, multiply by 1. That's going to give you 0.25. If you start off with 0.3, you can most certainly use up 0.25. You say 0.3 minus 0.25, that gives you the end. In fact, you don't even need to do this calculation to answer the first question, which reactant is the limiting reactant? And that, of course, would be, the limiting reactant would be hydrogen gas. Okay. Bound time method is easier. It's where you multiply and give more hydrogen. Yeah, okay. Look, if that's something you're comfortable with, that's fine. You can stick to that method, right? Again, I just prefer to teach the rice table because it's used so much. And for acids and bases, I really do prefer the rice table. And I feel like the rice table works well in acids and bases. But you are more than welcome to use any method that you learned, bow tie method or any other tables that you learned, or if you use basic stoichiometry, okay, then you are free to use those, okay? Particularly, yeah, if you understand the rice table, I would say stick to the rice table, okay? So, okay, which reactant is the limiting reactant? Okay, so in this case, it would be the hydrogen gas. Now they say, determine the mass of ammonia that can be produced. Okay, so this is easy. So one more concept that we need to understand, or one more thing that we need to note, is that in this reaction, in all limiting reactions, okay, you always start off with zero product, okay, because you have only reactants initially, okay. So since you only have reactants initially, right, you have no product. So initially you have zero product, okay, and then you can use the molar ratio to determine the change of the product, okay. So let's do that, because here it is a 3. Let's use this. It's a 3:2 ratio, okay. So we can use the 0.75 divided by 3 multiplied by 2 to give us the amount of moles we have in the change of NH3. Okay, so we say moles of H2 R2, the moles of NH3. What is this relationship? It is a 3:2 relationship where we have 0.75 moles of hydrogen, okay, which we want to convert to the molar ratio of 2 of ammonia. So we divide by 3 and multiply by 2. That's going to give us this amount. And here we get 0.5, or I'll put 0.50. Yeah, 0.50 moles of ammonia. Okay, so that's how we use that molar ratio. So here I add 0.5 moles. And of course, I'd end up with, okay, let's just leave out the moles, add that. And I end up with 0.5 moles as well. Okay, because I start off with 0. Remember, in the product, your change is always a plus, right? These are not positive and negative numbers. It just means to how do you get from initial to end, right? How do you get from initial change and then to end? Okay, so for reactants, you subtract because you use up reactants. And for products, you add because you form products. Okay, so you start off with 0 amount of product and you form. So this is the only place you can use molar ratio. You can use it right across, and you should use it right across. Okay, so once you have one of these amounts, you can get all of these amounts. So you can even get the change for NH3, right? This is how much actually reacts. And that's why it follows the molar ratio. That's why change is the only part that follows the molar ratio, because this is actually how much reacts using the 1:3 molar ratio and all of that. Okay, so we start off with 0 product, we form 0.5. So 0 plus 0.5 is 0.5. What do they want? They want the mass of ammonia that can be produced. We just calculated the moles of ammonia that is produced. So we now basically need to convert this moles using N is equal to M over M. This is for the ammonia, NH3. Okay. And now we can convert it. So 0.5 is equal to the mass divided by the molar mass of ammonia, which is 17. So it becomes multiplication. And the mass of ammonia produced when we do that calculation is 8.5 grams. Okay, so that's how we utilize Rice table. So the first part was to write down the initials, okay, understanding the information that's given in the written, okay, what part about it is initial, okay, we need to understand this is a limiting reagent. So even when they say an 8.4 gram sample of nitrogen reacts with 1.5 grams of hydrogen, we mustn't have the understanding that it completely reacts. So we mustn't initially assume it, okay. Always be wary and be careful and think to yourself, okay, does all of it react? Okay, and then you'll see they'll ask what is the limiting reagent, and you know, okay, I know for sure now that not all of it reacts. Okay, so those are initial amounts that do not follow the molar ratio. Okay, we then use a trial and error method to determine which one is the limiting reagent in our Rice table. Firstly, we treat the first one. So sometimes maybe the first one would work. But like I said, the more practice it is, you'll get better at it and you'll be able to do it in your head. Then you should get to a point where you can do it in your head, right? You'll take the initial amount of moles, right? You'll divide it by your own molar mass, multiplied by the own molar ratio, multiplied by the molar ratio that you want to check out. And you'll see that it's more than what you initially started off with. Then you start off with the other one. Okay, I'll treat this as my limiting reagent. So that's how we determined what the limiting reagent is. Okay, once we determine that, remember that in change, you can use the only place where you can use molar ratio, right? Because that's the only one that follows the molar ratio, because that's the change is what actually reacts and what actually forms, right? This information is not what actually reacts and what actually forms. That's just what we have initially, right? We're not sure if all of it is going to react. Okay, and then here we need to understand that at the end we have the excess and one is the limiting, and this is the product, right? This is the amount of product that we produce at the end, and that is the final question, the mass of ammonia that can be produced. Okay, so we can use change to get even the amount of product formed, and we know we started off with 0. Okay, they might specify in a question they start off with a certain amount of product, but generally it's 0. We form that much and we end up with that much, and that's our product, and that's how we got this. Okay. Okay, cool. If you guys have any questions, please let me know. What I've decided to do is just leave at least 5 to 10 minutes at the end of the lesson. If you want to unmute yourself, you can raise your hand and you can even ask your question verbally. You can ask your question in the chat, but we will try and dedicate the last portion of our lesson to questions. So if there's anything that's still confusing you from this, or if you're not sure about something, or if you have a question, please, now is the time to ask it. Okay, while we are waiting for people who have questions, if there's any, to ask questions, I was going to say something, but now I forgot. Yes, I would recommend that you practice questions. I think what we're going to do is we're still going to do another question of limiting reagent. So in the next lesson, we'll try and finish percentage purity, percentage yield. Okay. And I have this question which I wanted to do, but of course we don't have the time, but hopefully in the next lessons we can complete it. Yeah. Okay, I'm still here. If you guys have any questions, the lesson will be open for the next 5 minutes. Those who don't have any questions or don't want to wait to see if anyone has any questions, you are free to leave if you'd like. Okay, doesn't seem like anyone has any questions, so let's leave it at that. Thank you guys so much for joining. Have a good rest of your week, and I shall see you guys next week where we'll continue with stoichiometry. Okay, thank you. Jazakallah khair. Assalamu alaikum and goodbye.